Today we're learning about rotational velocity, Unit 5 of Physics C. We're doing a problem about a spaceship and the Earth. The problem says, a spacecraft of mass 1,000 kilograms is in an elliptical orbit around the Earth, as shown above. At point A, the spacecraft is at a distance RA equals 1.2 times 10 to the 7th meters from the center of the Earth, and its velocity of magnitude VA equals 7.1 times 10 to the 3rd meters per second is perpendicular to the line connecting to the center of the Earth to the spacecraft. The mass and radius of the Earth are ME equals 6 times 10 to the 24th kilograms and RE equals 6.4 times 10 to the 6th meters, respectively. Determine each of the following for the spacecraft when it is at point A. So for problem A, where it says the total mechanical energy of the spacecraft, assuming that the gravitational potential energy is 0 at an infinite distance from the Earth. Finding total mechanical energy, we have to find the kinetic energy and the gravity of the Earth. So for the equations, we have, for kinetic energy, we have half of mv squared, and then we have for the gravity, gravity constant with the first mass, the second mass over the radius.
Sorry for sneezing.
So then when we plug in the numbers here, we get half of the mass of the spacecraft times the magnitude, which is then subtracted by the gravity of the Earth. So we have,
boy, that's not the gravity of the Earth.
Okay, gravity constant, we take the mass of the spaceship, and then we're going to take the mass and radius of the Earth, or the mass of the Earth, and then we're going to divide it by the radius of the Earth. And then once we get the kinetic energy and the gravity, we subtract the kinetic energy by the gravity, which gives us the total mechanical energy, which is 8.1 times 10 to the 9th joules. Negative 8.1 times 10 to the 9th joules.
So for part B, we're finding the angular momentum of the spacecraft about the Earth. And to do that, we're going to use the formula L equals mvr, okay? M is the mass of the spacecraft, which is 1,000 kilograms. V is the velocity, which is 7.1 times 10 to the 3 meters per second. And then R is the radius of the Earth, which is 1.2 times 10 to the 7th meters. And then when you do that, you get that, which is the answer.
What's the answer, Aaron?
8.5 times 10 to the 13th kilogram meters squared per second.
So later, the spacecraft is at point B, on the exact opposite side of the orbit at a distance RB equals 3.6 times 10 to the 7th meters from the center of the Earth. So for C, we're going to determine the speed of VB of the spacecraft at point B. So we have to find the angular momentum. So we're using the equation mvr, but we're using the one from the first problem from when it's at point A, and then we're going to use it for point B. So then we do the math problem. And we have 7.1 times 10 to the 3rd multiplied by the radius equals the second velocity from one spaceship's over here times
No, this is
the RB over here. And then you multiply these two and then divide it by this, which gives you the velocity of the spaceship at point B, which is 2.4 times 10 to the 3rd meters per second.
We're recording.
Okay, so we're going to try and find the velocity of the spacecraft. So by doing that, we're going to use sum of the forces equals mv squared over r. And the total force is the gravitational force. So basically just set mv squared over r equal to the gravitational force. And then solve for v, and after all that stuff cancels, you get the square root of g m2 over r. And then you just plug in the numbers for that. So you got that constant, the mass, the Earth, and then the radius of the Earth. And you get the velocity, which is 5.8 times 10 to the 3 meters per second.
Yeah.
Alright, so now we're trying to find the minimum speed of the spacecraft at point A if it is to escape completely from the Earth. So what we're going to do here is going to use kinetic energy and the gravitational energy, and we have to make it equal to 0. So we use the equation as half mv squared plus the gravitational energy, which is gm1 m2 over r. And so then we have to make it equal to 0, so we move the gravitational energy equation over to the other side, and then you take the square root of the gravitational energy, and then on the other side it comes out to v, and then you take and you go 2 times the gravitational constant multiplied by, what is that again, Aaron?
Mass of the Earth.
By the mass of the Earth over the radius, and it gives you the answer 8.2 times 10 to the 3rd meters squared.
Meters per second.
Wearing black t-shirts. Sometimes they will tattoo themselves.
This blurring line. Starlight and wake, a change on blind. Starlight through us, despite what's right. One final fight for this.